Welcome to Chapter 6 Recitation Problems. Okay, so today we're going to talk about thermochemistry. Thermochemistry. So this has to do with temperature and temperature of objects and heat and energy. Some important things you'll need to know is include you'll need to refer to table 6.4, and that's on page 257. You don't have to memorize this table, but it does have a lot of specific heat capacities. Specific heat is the amount of heat, and when we talk about heat, it's a Q. The amount of heat required to raise 1 gram of substance 1 degree Celsius of water temperature. So comparing like water specific heat, you have 4.18 joules per gram per degree Celsius, because that's the amount of heat in joules to raise 1 gram of water 1 degree Celsius. If you compare this with copper, so specific heats are specific to the substance or the element. This one is 0.385 joules per gram degree Celsius. And if you notice the difference in these numbers, 0.38 versus 4, what does that tell you? That's telling you that copper will heat up quickly and will also cool down quickly. That's why a lot of your pans are lined with copper, whereas water has a very high specific heat capacity, and that's why a body of water takes a while to warm up 1 degree Celsius and also to decrease by 1 degree Celsius. You'll be using this equation, Q equals M times the specific heat times the change of temperature. And one other thing that's kind of important here is the state functions. So your state functions are T, energy, pressure, and volume. And when you have state function, which are capital letters, they're independent of path, and that means this delta, which is the triangle, is basically the final minus the initial. And so you can do that with pressure, temperatures, energies, and sometimes those will be formulas that you will want to use. Other formulas for this chapter include work equals negative P delta V. So if you notice, like the little q and the little w, they are dependent on the path of energy, but the big P and the V and the T here are state functions, so you can do delta T or delta V. But we'll talk about what this minus sign means. That's important. And another conversion factor you need to know for units is 101.3 joules equals 1 liter times atmosphere. That will be important. And the problems for this chapter will be for recitation. Your participation points are 6.2, 6.4, 6.6, and 6.7. The first problem is 6-1. To work this problem, you need to kind of review on page 265. You need to understand the terms of enthalpy. So delta H is enthalpy. And what is interesting is delta H equals the heat of your reaction at constant pressure. And that's what this little subscript P means. It's constant pressure. Most of the things you do in chemistry would be at constant pressure because we're at 1 atmosphere and you'd be doing it at your bench or whatever. So the first thing you're going to do in this problem is you're going to convert grams to moles for your sodium metal. So we have sodium metal here, and when you consider the enthalpy of a reaction, so every reaction has a delta H associated with it, and that delta H can be used as a conversion factor for how many moles. So like 2 moles of sodium, 2 moles of HCl, 2 moles of sodium chloride, and you can make that into a conversion factor. And there are a couple ways to calculate delta H of reaction using Hess's law and the delta H of formation that's talked about in chapter 6. Now, the other thing you can tell about delta H of a reaction, if it's less than 0, that's negative, and a negative delta H is an exothermic reaction. So that's important to know. That means heat is giving off to the surroundings. Your classic exothermic reaction is a bonfire. So when you're catching and burning anything that's carbon with oxygen, producing carbon dioxide, the combustion reaction in water, that is an exothermic reaction. It gives off heat. Endothermic reaction would be delta H is greater than 0. So if delta H is greater than 0, it's an endothermic reaction, and those will feel cold to the touch because they'll be pulling heat in from the surrounding. Now, for this reaction, you basically want to convert 0.834 grams of sodium metal into mole. And so you look at the periodic table and you see that 23.00 grams of sodium equals 1 mole of sodium. And then that gives you 0.0363 mole of sodium. So let's just read this now. When you add 0.0363 moles of sodium metal to an excess hydrochloric acid, you find that 8,670 joules of heat are produced. What's the enthalpy of the reaction as written below? So now we can start with our given here, 0.0363 moles of sodium. This is just showing you how you can use this enthalpy are produced. So what you can do with this problem is it's telling you that 8,670 joules of heat are produced if you have this much material. So actually what you want to do is you want to take the 8,670 joules, we'll start over here, 8,670 joules, and that is per 0.0363 mole of sodium. However, you have 2 mole of sodium in this reaction, and it wants to know the enthalpy of this reaction. So this is going to be multiplied by 2 mole of sodium. That's going to cancel out your sodium. And most of these delta H's are written in terms of kilojoules, so we'll just go ahead and convert 1,000 joules into 1 kilojoule. And when you run that through your calculator, you get 477.7 kilojoules. And that is your delta H for this reaction for 2 moles of sodium metal. This is problem 6-2. What you want to do here is you want to use amount of heat Q times heat capacity times delta T, and basically you're going to solve for C 29 degrees, since it increases by 29 degrees, this is already giving you a delta T of 29.0 degrees Celsius. And 3,693 joules is your heat. So 3,693 joules equals C times 29.0 degrees Celsius. You isolate your variable C, so you take 3,693 divided by 29 degrees, and you get a 127.3 joules gram degrees Celsius, because that's the units for C. Now here, they actually give you a specific heat, or they want you to calculate a specific heat, and they give you the mass. So you want to use Q equals M times your specific heat times your delta T, and you're going to put in your 3,693 joules equals 331 grams times CS times 29.0 degrees Celsius. And that's going to work out to be 3693 equals 9599 CS when you, and don't forget your units, which is grams times degrees Celsius. You're going to divide both sides to isolate the CS, which you're solving for. You're going to divide both sides by 9599 grams degrees Celsius. 9599 grams degrees Celsius. Keep the joules there. And that works out to be CS equals 0.385 joules per grams degrees Celsius. And that would be copper. And those specific heats are characteristics of certain metals. This is problem 6-3. And so it's asking how many grams of liquid sodium is needed to absorb. So the important thing is when you see the absorb, good things to note is this is an endothermic. So you're going to be looking for a positive delta H. How many grams needed? Increase no more than 10 degrees Celsius. So your delta T, we're just going to set equal to 10.0 degrees Celsius. Our specific heat capacity here, and I guess it's at a different pressure maybe, that's why you have the CP, 30.8 joules per Kelvin times mole, which is a little unusual, but that's the way it's given to us, so we'll make sure we use those units. And we have how much heat. See the megajoules? So our Q equals 7.00 megajoules. So the first thing I'm going to do is I'm going to convert megajoules into joules. And then after I do this, I'm also going to convert, because this is a Kelvin, and I want to use that in my equation, which I'm going to use Q equals M CP times delta T. I'm going to use these units, so I need to convert megajoules into joules. I need to convert degrees Celsius into Kelvin. And I need to do that. So degrees Celsius, what do we have? We have 10 degrees Celsius. We add 273 Kelvin, and that's going to be 283 Kelvin. Megajoules, so basically 7.00 big MJ. That is big M, mega, is bigger than our base unit, so yeah. So basically, for 1 megajoule, you have 1 million joules. And so that's going to be 7 million joules. And then we're going to put this in our equation. So 7 million joules equals mass, which is what we're going to solve for. We're given 30.8 joules per Kelvin mole, and we're given our temperature that we converted to 83 Kelvin. We put this in our calculator. We multiply these two terms. The Kelvins cancel out. We divide both sides. So we'll divide both sides basically by 8716.4 joules per mole. 8716.4 joules per mole. The joules will cancel out, and you are given 803.08 mole equals your mass. The question asks how many grams. So we will then use our molar mass, and we'll go from 803.08 mole of sodium and over 1. For 1 mole of sodium, we have 23.00 grams of sodium, and this equals out to 1.85 times 10 to the 4th grams of sodium liquid that is required to absorb 7 megajoules of energy. This is problem 6-4. Okay, so this is a pressure volume work, and the formula that you need to know is work equals negative P times delta V. You can read about this on page 261. And you see the words expands. You need to associate a gas expanding that does work. So it's doing work on the surrounding. If it's expanding, so this means it's lost energy to the surrounding the system has, and this will always be negative. Okay, so if a gas expands, it's going to be a negative work, and if a gas compresses, work is going to be positive. And it works out to be because of the delta V term, which is the V final minus V initial. If it expands, then this term is going to be positive. If it compresses, this will be negative. And because you have a negative in the equation right here, then that makes the overall work positive in that situation. Okay, so what do we see? We see that we're going to need the conversion factor 101.3 joules equals 1 liter times atmosphere. And we are given 69.8 milliliters is the V initial. And we're going to want to convert this to liters, so we do 69.8 milliliters. And there's 1,000 milliliters in 1 liter, which works out to be 0.0698 liters, and this is the V initial. We're going to look for the V final. What is the final volume of the gas? We're also given a constant pressure of 783 torr. We need to get this into atmosphere, so you need to know 760 torr is 1 atmosphere. And when you do that math, you get 1.03 atmospheres. And then we can also go ahead and convert the 116.9 joules of work into liters atmosphere. So we have 101.3 Where is our conversion here? Joules per 1 liter atmosphere. And this ends up being 1.15 liters times atmosphere. And now we'll have everything in the correct units, liter atmosphere, so we can just plug and chug it in our formula. Work equals negative P V final minus V initial. And we put in our variables here. So work is Q, and that's going to be negative, I'm sorry, that's not negative. Actually it is, because why? Because it expands, so we know that it's going to be negative. So the answer is negative 1.15 liters times atmosphere equals the negative from the equation. The pressure is 1.03 atmospheres, which we did our conversion there, and then V final is what we're looking for, and then we're going to subtract V initial in liters, and we did this conversion here, so minus 0.0698 liters. When you put that in your calculator, you get 1.19 liters equals your final volume. And then the question is, did that expand? And the answer is yes, it did expand, because it started out at 0.0698 liters. Just to make this a little clearer, just in case some people might need it for the math, to work this, you would do negative 1.15 liters times atmosphere equals, and then you would multiply each term. So negative 1.03 atmospheres times VF, and then if you take a negative 1.03 times a negative 0.0698, a negative times a negative is going to give you a positive, so that's going to be in plus 0.071894, and you keep your units liters times atmosphere. In order to, since this is addition right here, you can subtract that from both sides of your equation, liters times atmosphere minus 0.071894 liters times atmosphere. That will cancel this out, and you will get a negative 1.22 liters times atmosphere equals negative 1.03 atmospheres times VF. Now you want to isolate the VF, so you're going to divide both sides because they're multiplied together by negative 1.03 atmospheres. So you do this by both sides on 3 atmospheres. This cancels this out, atmospheres cancels out, and then VF equals the answer 1.19, which is a positive because a negative divided by a negative is a positive, and you have liters. Next problem is problem 6.5. And once again, I'm going to refresh this. If you have expansion of gas, you need negative work. So the system is doing negative work because it's losing energy, heat to the surrounding. If your gas is compressing, this is going to be a positive work. You need to know those terms and understand. Okay, so basically you're using W equals negative P delta V. And this problem is showing you that the little w, work, is dependent on the path. So you can't just do the state function where you take the final minus initial. And so the way this problem is trying to show you that is first you want to calculate the work if your gas is expanding from a final volume of 10 from initial 1. So what's your delta V? Your final minus initial is going to be 10.0 liters minus the 1.00 liters. So your delta V here is going to be 1.00 liters. And your external pressure here is 1 atmosphere. So basically you go work equals negative 1.00 atmospheres times 1.00 liters. And that's not right, because I'm sorry, what is 10 minus 1? That is 9. So this should be 9 liters. And when you do this, 9 times a negative 1, let's put that right here. 9 times a negative 1, work equals a negative 9 work equals a negative 9.00 liters atmosphere. And we like to convert this actually to joules. So let's do the conversion real quick of negative 9.00 liter atmosphere. And we have, for 1 liter atmosphere, we have 101.3 joules. That works out to be negative 911.7 joules. Now, if we do the same, we're going from overall, we're going to move the volume change, 9 liters. We break it up into 2 steps. So we'll call this step 1 and then step 2. So in step 1, you're using the same formula, work equals negative P delta V, but you're going from, you've got an external pressure now of 5 atmospheres, so work equals negative 5.00 atmospheres. And you're going to a volume of 2 liters. You're still initially at 1 liter. So VF here minus VI is 2 minus 1 liters. So this would be, the delta V here would be 1 liter. So we'll go ahead, and that works out to be negative 5.0 liters times atmosphere. And then let's convert this. So negative 5.00 liter atmosphere over 1. For 1 liter atmosphere, we have 101.3 joules. This works out to be negative 506.5 joules. And the negative, once again, is because the gas is expanding. The final volume is larger than the initial. Now we couple this. We're going to couple this with the second step. And then we're going to add these two together. We then let the gas expand to 10 liters against a constant external pressure of 1 atmosphere. So number 2, what's our delta V? 10 liters, and we're at 2 liters. So this is going to be 8 liters. And we're doing this one at a pressure of 1.00 atmosphere. So I've got negative 1.00 atmosphere times 8.00 liters. This ends up being work equals negative 8.00 liters times atmosphere. And if we convert this using 1 liter atmosphere equals to 101.3 joules, we get negative 8 times 101.3. Once again, the negative's there because it's expanding and giving off heat to the atmosphere, the surrounding. That's negative 810 joules. And if we add this with our work number 1, because we've got to add it together to get our overall, if it's done in 2 steps, so negative 506.5 joules plus negative 810.4 joules equals negative 1316.9 joules. Now, the point of this exercise is to compare. We're going the same volume expansion to a final 10 liters from 1. But if you do it over 2 steps, we do work of 1,316.9 joules, whereas here we did in just 1 step at 1 pressure, and we got negative 911.7 joules. So it's dependent on the path. This is problem 6-6. And, okay, so we've talked about gas expanding to do work. So here's our work equals negative P delta V. And we've talked about delta V is the final minus the initial. And so what expands? Solids don't expand. Aqueous solutions don't really expand. We're talking about gases. So when you have a chemical reaction, you've got to look at your products minus your reactants. And you need to talk about your gas moles. Because if your final, so if your products are greater than your reactants, then this delta V is going to be greater than 0. It's going to be positive. If you have a positive delta V times a negative P, your work ends up being negative. And that would be an expansion of volume. So the question is, what do these systems do work on the surrounding? That means you have to have a negative work. That's what you're looking for. And the only way you're going to do that is if your products, your volume, your gas molecules are greater than your reactant. So here you just look at your coefficients and you say 3 moles, so you're going to do the product minus your reactant. So you got 3 minus 4. It's going to be a negative 1. A negative value in your delta V times a negative, that's going to be a positive work. That's not going to give you what you want. Here you have 3 minus 3. So your delta V term is going to be 0. That's going to give you a work equals 0. That's not what you want. You want a negative work. Here you have 4 minus, what is that? 3, 4, 5. So 4 minus 5 is a negative 1. So once again, you're going to have a positive work, just like the first example. And the last one, you have 4 minus 3, which is a positive 1. So you have a positive mole of gas in your delta V. That's going to make that positive term. And work equals negative P times a positive delta V is going to give you a negative work. And the negative work is what you need. So the bottom one is the correct answer. This is problem 6-7. This is Hess's law. Hess's law, you can always recognize it because it has like all these equations, and then it has you want the enthalpy for the following reaction. And the way I do this is very systematic. Excuse me. I look at the final reaction and I just work my way from left to right. And then I rearrange the 4 equations at the top, however, to give me this overall equation. So the first thing I do is I look for 2ms. Okay, there it is, 2ms. It's on the right side of the equation, on the reactant side, and it has the correct coefficient in front of it. So I am not going to do anything to that equation. I'm going to leave the delta H1 alone. If I do something to that reaction equation, I have to do the same thing to the delta H calculation. Okay, the next thing I'm going to do is I'm going to go to this 3Cl2 gas term, and I'm going to look for it. And I'm going to say, okay, I see a Cl2 gas term, and is it on the correct side of the reaction arrow? Yes, it's on the reactant side. Okay, so I don't have to flip the reaction. That's good. However, it needs a 3. So I'm going to have to multiply a 3 through this reaction. So every coefficient was 3 times 2, 6. And then I'm going to have to do 3 times my delta H. So that's going to be delta H3 is actually going to be 3 times negative 1,845.0 kilojoules. So, because overall I'm going to have to calculate, I'm going to have to sum up all my delta H's. Okay, so I took care of that, and now I'm going to go to this last one. I'm going to look for MCl3 solid. Well, that's MCl3 aqueous, so that's not what I want. Okay, so here's MCl3 solid. Is it on the correct side? No. So I'm going to have to rewrite this equation to be MCl3 aqueous goes to MCl3 solid. And when I do that, I have to reverse this sign here on the delta H. So this is going to be delta H4 equals, instead of a negative, it's going to be a positive 197.0 kilojoules. Okay, so now I do have it on the right, the correct side of the reaction arrow, which is the product side. But I need a 2 coefficient. So I'm going to multiply both sides by 2. And when I do that, I'm going to have to multiply the 197 kilojoules by 2. Now, I'm going to go through and see if I can cancel out all these other compounds that are not in this overall equation. So I'm going to be looking to make sure if I find them on the reactant side, can I find them on the product side, and do they have the same coefficient? So the first 2M solid is what I need, so no worries there. Okay, what about this HCl aqueous? So where is that? That is right here. So the nice thing is I have that on the reactant and then on the product, but the problem is one of them has 6 and the other one has 1. So if you added up these total equations, you would have 5 HCl aqueous on the reactant side. So what you're going to have to do is you're going to have to multiply this by 6, which means you got to do your delta H2 equals 6 times negative 74.8 kilojoules. Now, what's nice about that is I can cross out these two. I'm going to go to the 2MCl3 aqueous, and that's on the product side, and I have 2MCl aqueous on the reactant side. So I can cancel these two out. That's good because they're not in my overall equation. 3 hydrogen gas. I'm going to look for 3 hydrogen gas. So I've got on the reactant side and the product side, so those cancel out. And then I'm going to go to HCl gas, and I see 6 HCl gas here and 6 HCl gas there, and we rewrote this equation here. So it looks like I'm good. So if you add these up, you would have 2M solid. These are all X'd out. 3Cl2, this is on the reactant side, reaction arrow, and then 2MCl3. So when you add all these up, they total this final equation here. So we are ready now to add up delta H1 through delta H4. So we're just going to do 1 plus 2 plus 3 plus 4. And that is going to give us our overall delta H. So it's going to be negative 888.0 kilojoules plus this one here, we multiplied it by 6. 6 times negative 74.8 kilojoules plus this one we multiply by 3. 3 times negative 1845.0 kilojoules. And then plus this one, reverse the sign and multiply it by 2. 2 times 197.0 kilojoules. When we add all of those 4 delta H's up, our answer is delta H overall is negative 1496.3 kilojoules. And that is Hess's law, which is independent of path because it's a state function with a capital H.